In Activity 5 from Section 29, we are creating models from contextual situations. And then we're going to be using those situations to analyze and go a little bit further and actually find some values. So the first problem, we have a town's population is growing by 1,700 people each year. So right there, that number 1,700 increasing every single year, that indicates to me that this is a linear relationship, that we're going to add that same number every single time. So in question 1, it says if the town's population is currently 23,000, write a function p in terms of t, which represents the population of the town t years from now. So our function would be p of t, the population with respect to time, equals 23,000, that's our starting value, plus 1,700 times t. Again, 1,700 is our slope, and then we've got our time, which is measured in years. In question 2, then, we're going to take that model, and we want to find the population of the town 5 years from now. So in this case, we know that t is equal to 5. We plug 5 in, go ahead and simplify it, and go a little bit further, and we get 31,500 for the population. In the next question, we have a very similar situation that we have the town's population growing, but now it's by 3% each year. So it's a growth problem, but we know it's going to be exponential because of the fact that it's growing by 3% every year. So if the town's population is currently 23,000, we want to write p of t, or a function p in terms of t, which represents the population of the town t years from now. So we take p of t equals 23,000, again that's our initial starting point, times 1.03 to the t. 3% growth, we add it to 1 to get our growth factor. And then from there in question 4, 5 years from now, we'll have to round because we're dealing with people. So we want to make sure we round to the nearest whole person, 26,663. And the other two questions from this activity are kind of the same basic thing. Again, it's just a matter of differentiating between exponential versus linear. And in question 5 and 6, we're investing $300 in a bank that's offering 5% interest. Again, a percent growth usually indicates to us that that's going to be an exponential function, and we're adding to the value when we've got interest. So we take our initial value times 1.05 to the t, because that's our measure of variable. And then number 6, just simplify it. Plug that number in and go. And number 7, same basic situation. We have $300 invested, but now instead of 5%, it's a $5 interest every year. So again, a linear relationship, we got 300 plus 5t. In activity 6, we're given a verbal description of a situation, asked to fill out a table, decide if it's linear or exponential, then write a function, and use that function to calculate a future value. So in this particular situation, we've got a population of rabbits doubling in size every month. At the beginning, there are 10 rabbits in January, which we are calling month 0. And that's a key piece of information, that January is month 0. Normally it's month 1. And you'll see why that's important in question number 4. So to complete the table of values, we take our population, which starts off at 10, and we double it every month. 20, 40, 80, 160, and so on. So we're multiplying by 2 to get our next values. So that is an exponential relationship. The reason we know that is because we're multiplying all of our values by 2 to get the subsequent population. So we're writing the function p in terms of m, which represents the scenario. We have p of m equals 10, which is our initial starting point. That's what we started with, times the growth factor to the variable. And our growth factor is 2, and our variable in this case is m, which stands for months. And for question 4, which month is the first in which the rabbit population exceeds 1,000? So we're essentially just going to continue our pattern. I think that's probably the easiest thing to do. We could also set up a table in our calculator with this new function and find out when the population is above 1,000. Well, that happens in the 7th month. But again, normally the 7th month would be July. But the fact that January was month 0 makes that actually August for our month 7. So again, this is January, February, March, April, May, June, July, August. And in question number 2, we got a population of tortoises increasing by 20 every month. We're adding 20 every single month, so that would be a linear relationship. And our justification is that we added 20. Question 7 says write a function p of m in terms of, p in terms of m, which represents the scenario. So p of m is your initial value, 10, plus what you're adding every month, that's your slope, times the number of months. Now for this one, to solve it, continuing the table would be a very bad choice because it would take a really long time to get to the values that you want. So probably the easier thing to do is find out when m, when we plug that in, would give us 1,000. And that would happen in the 49.5 month. We're going to round that up, no matter what it is, if it's 49.2 or 49.3, because it doesn't happen until the next month. So our final answer there would be the 50th month. And we're not going to go back and figure out, that was 4 years and 2 months, because that's kind of defeats the purpose of the question. 9 through 12, we're dealing with a population of dogs decreasing by 12 every month, so subtracting 12 gives us that linear relationship. Once again, we can continue that table if we want to, because the numbers are relatively small. And then the last one here is dealing with the population of insects, and it's cut in half every month. So this is where it gets a little bit weird, because there's 4,000 in July, which we're calling that month 0. It doesn't make sense to have a starting point of January in this case if we're talking about the population of bugs decreasing, because we know that in January there's fewer insects out there. So July would have a fairly large population, then August, September, and so on would decrease. It would represent a exponential relationship because we're multiplying by 1/2. And there is our function, 4,000 times 1/2 to the m, or 0.5 to the m if you will. And that will end up being March because it's 8 months from July, and that's when the population will reach 20 insects.